In this video, we'll be continuing our discussion on piecewise-defined functions. We'll be looking at more examples to get us familiar with evaluating piecewise-defined functions, graphing them, and finding their domain and range. For our first example here, we have the function named f. When we input x, we'll get different outputs depending on what value x is. If x is not equal to 2, to get the output, we would use the formula 1/2 x plus 1. If my input x is equal to 2, then our output is -1. So in this piecewise defined function, the input x not equal to 2 is my first piece. The input x equal to 2 is my second piece. Let's get some practice evaluating this piecewise defined function. If we want to compute f of 0, meaning find the output when my input is 0, well, we first have to decide, is the input 0 in our first piece or the second piece? Since 0 is not equal to 2, this input is in our first piece, which means to compute the output, we would use the formula 1/2 x plus 1. So our output here is going to be 1/2 times 0 plus 1, which gives me 1. To evaluate f of 1, we want to find the output when the input is 1. Again, we need to decide whether 1 is in the first piece or the second piece. Since 1 is not equal to 2, this is in the first piece, which means I would use the formula 1/2 x plus 1 to compute the output. So this is going to be 1/2 times 1 plus 1, which gives me 1.5 or 3/2. Next, we want to evaluate f of 2, which means find the output of the function when I input 2. Is it in the first piece or the second piece? Since my input is 2, we are in the second piece, which means to get the output, we would use the formula -1. So f of 2 is just -1. Lastly, we have f of 3. So when I input 3 into my function, is it in the first piece or the second piece? Since 3 is not equal to 2, we're in the first piece, which means we would use 1/2 x plus 1 to calculate our output. So f of 3 is equal to 1/2 times 3 plus 1, which is 3/2 plus 1, which gives us 2.5 or 5/2. Next, let's try to graph this function. Now, the first thing we want to do when we graph piecewise defined functions is to use vertical dotted lines to separate the different pieces. For our first piece, we have x values that are not equal to 2. So what I'm going to do is I'm going to draw a vertical dotted line right at x equals 2. This dotted line tells me that as long as I'm not on the dotted line, I'm going to be in our first piece, which means that my function will behave like 1/2 x plus 1. For our second piece, we have x equals 2, which is what is on this dotted line. And on this dotted line, since my function is -1, we just have the point 2, -1, which we'll place on our graph. Again, our first piece is x is not equal to 2, meaning that when I'm on the left-hand side of this dotted line and when I'm on the right-hand side of this dotted line, my function behaves like 1/2 x plus 1. So essentially, on either side of the dotted line, I'm graphing y equals 1/2 x plus 1. So let's try to graph this. Remember that if you're ever unsure of what a certain graph looks like, you can always make a table of values. So let's make a table. The x values that I'm going to select here are going to be some on either side of our dotted line. So let's do 0, 1. We'll also include the x value on the dotted line, so include 2, let's do 3, and then 4. To get the corresponding y value, we use the equation y equals 1/2 x plus 1. At x equals 0, we've actually computed this already. 1/2 times 0 plus 1 gives us 1. When x is equal to 1, again, we've computed this previously. 1/2 times 1 plus 1 gives me 3/2 or 1.5. Next, when x is equal to 2, we have 1/2 times 2 plus 1, which is 1 plus 1, which gives us 2. When x is 3, We've evaluated this previously. 1/2 times 3 plus 1 gives us 5/2. And then lastly, when x is equal to 4, we have 1/2 times 4 plus 1, which is 2 plus 1, or 3. Now that we've completed our table, let's plot our points. We have 0, 1, we have 1, 3/2, we have 2, 2, we have 3, 5/2, and then 4, 3. Let's connect our points here with a straight line. Now, before we can move on to the second piece of our graph, we need to check the boundary. So at the boundary, x equals 2, we want to decide whether or not this point here, 2, 2, is actually on my graph. Well, when x is equal to 2, this is not part of the first piece, so I would not be using the formula 1/2 x plus 1 to get the output. That's why at this boundary, we're going to replace this point with an open circle. So now we've fully illustrated our first piece. On either side of x equals 2, we've drawn the graph of y equals 1/2 x plus 1. Now let's move on to our second piece. Our second piece is just for x equals 2. At x equals 2, we know that the output is -1, so we have the point 2, -1 here. So I'm going to place that point on my dotted line. Now that we've drawn our two pieces, we're done. Now the last thing we want to do is determine the domain and range for this function. Remember that the domain of this function are the inputs that you can plug in. For piecewise defined functions, we want to look at the x values that are in each of our pieces. So we'll start by drawing a number line, and we'll illustrate on the number line the x values in each of our pieces. In our first piece, we're looking at x values not equal to 2, so put down 2 on the number line and draw an open circle around it. And what we want are the x values on either side of 2. For our second piece, we're looking at the x value equal to 2. So on our number line, we end up filling in this point at 2. So looking at what's covered on our number line, we see that we have all of the x values, which means that our domain in this case is going to be -infinity to infinity. To determine the range of our function, we want to look at the points on our graph and see what y values we have. If we trace our graph to the left here, we see that our graph keeps on going down forever, so there's no lower bound on my y values. So we'll start with -infinity. If we trace our graph to the right, we see that our graph goes up indefinitely, so there's no upper bound for my range. So I'm going to put +infinity on this side. However, we don't have a point with every single y value between -infinity to infinity. As we're going along this line, we see that there is a hole here, meaning we're missing a point with y value 2. So my range is actually going to be -infinity to infinity, except y equals 2. Let's now take a look at another example. In this example, we're working with a function named g. The output of our function depends on the x value. If our input is less than -2, the output is -1. If my input x is between -2 and 1, the output is -x² plus 3. And lastly, if my input x is greater than or equal to 3, then my output is 2x minus 6. Let's start by getting some practice with evaluating our function. If we want to evaluate g of -3, we want to find the output of our function when the input is -3. So what we need to do is decide which piece -3 is in. Is -3 in the first piece, second piece, or the third piece? Since -3 is less than -2, we're in our first piece, which means the output is going to be -1. So g of -3 is -1. For g of 0, we're looking to find the output of our function when the input is 0. So once again, ask yourself, is 0 in the first piece, second piece, or the third piece? Since 0 is between -2 and 1, it's in the second piece, which means to get the output, we would use the formula -x² plus 3. So g of 0 is negative 0 squared plus 3, which gives us just 3. And then lastly, let's compute g of 4. What's the output when I input 4 into my function? 4 is in the third piece of my function because 4 is greater than or equal to 3, which means to get the output, we would use the formula 2 times x minus 6. So g of 4 would be 2 times 4 minus 6, which gives us 8 minus 6, or 2. Next, let's graph this function. The first thing we'll do to graph this function is to separate the different pieces using vertical dotted lines. Our first piece is x values less than negative 2. So let's draw a dotted line at x equals negative 2. So for all of the x values to the left of this dotted line, our function behaves like negative 1. Our second piece consists of x values between negative 2 and 1. We already have a dotted line on this left boundary at negative 2, so we also need a dotted line on the right boundary at 1. So for the x values between negative 2 and 1, our function will be behaving like negative x squared plus 3. Our third piece consists of x values that are greater than or equal to 3. So let's draw a dotted line at x equals 3. Now for these x values on the right of this dotted line, we know that our function will behave like 2x minus 6. Let's write down what we'll be graphing on each piece. Remember, on the first piece, our function behaves like negative 1, so we'll be graphing y equals negative 1 on this leftmost piece. On the second piece, for x values between negative 2 and 1, our function behaves like negative x squared plus 3, so we'll be graphing y equals negative x squared plus 3 on that middle piece. And then for our third piece, for x values greater than or equal to 3, our function behaves like 2x minus 6, so we'll be graphing y equals 2x minus 6 on this rightmost piece. So let's start by graphing this first piece, y equals negative 1. Remember that the graph of y equals a number is just a horizontal line. So we're going to be drawing a horizontal line at negative 1. Before we're done with graphing this first portion, we need to go to the boundary and decide whether we have a filled-in point at the boundary or an open circle. Namely, we want to ask ourselves, does my function behave like this horizontal line at the boundary? Well, to decide that, we want to look at the inequality symbol of our first piece. Since the inequality symbol is strictly less than negative 2, my function doesn't behave like negative 1 at x equals negative 2. So we're going to replace this endpoint here with an open circle. Let's now move on to our second piece. Here we want to graph y equals negative x squared plus 3. Now, if we don't know what the shape of this is, we can always make a table of values. The x values for this second piece are the x values from negative 2 to 1, and we want to make sure to include the x values on the boundary. So we'll put down negative 2, negative 1, 0, and 1. So for each of these x values, we can get the corresponding y values using the formula negative x squared plus 3. Plugging in negative 2, we have negative of negative 2 squared plus 3, which is negative 4 plus 3, or negative 1. Plugging in negative 1, we have negative of negative 1 squared plus 3. That's negative 1 plus 3, or 2. Next, when x is equal to 0, we've computed this already. Negative 0 squared plus 3, we know that that is 3. And then lastly, when we plug in x equals 1, we have negative of 1 squared plus 3, which gives us 2. So let's plot our points. We have negative 2, negative 1. We have negative 1 comma 2, 0 comma 3, and 1 comma 2. Connecting these points gives us the following shape. The last thing to do is decide whether or not we want to include the points at the boundaries of our interval. On the left boundary here at x equals negative 2, we want to ask ourselves, do we have the point negative 2 comma negative 1? Looking at our inequality here, we see that negative 2 is part of the second piece. So our function behaves like negative x squared plus 3, which means that we have the point -2, -1 as part of our graph. So even though initially this point was not part of my graph because it was not included in the first piece, it does end up being filled in because it is a part of our second piece. So now let's look at our right boundary at x equals 1. We want to ask ourselves, do we have the point 1, 2 as part of my graph? Looking at the inequality of our second piece, we see that 1 is not a part of the second piece, so our function would not behave like -x² + 3 there. So we're going to take that right endpoint, we're going to replace it with an open circle. So now let's move on to our third piece. For our third piece, we're looking at graphing y equals 2x minus 6 for x values greater than or equal to 3. So once again, we can make a table of values for y equals 2x minus 6. Our third piece consists of x values that are greater than or equal to 3, so let's put down the x values 3, 4, and 5 on our table. To find the corresponding y value, we use 2x minus 6, so plugging in 3, we have 2 times 3 minus 6, which is 6 minus 6, or 0. For x equals 4, we've computed this previously. 2 times 4 minus 6 gave us 2. And then lastly, when we plug in x equals 5, 2 times 5 minus 6 gives us 10 minus 6, which is 4. Plotting these points here, we have 3, 0, 4, 2, and then 5, 4. Let's now connect these points with a straight line. One last thing to do is look at the boundary at x equals 3. Is this point 3, 0 included in my graph? Looking at the inequality for our third piece, we see that 3 is included in our third piece. So this should be a solid point at 3, 0. Remember that when we're deciding whether or not to include a point on the boundary, we want to look at the inequality symbols of our pieces. If it's a strict inequality without an equals to sign, that means we're not including the point, which means we're going to use an open circle. However, if there is an equals to symbol, that means we're going to include the point and we use a solid point. There's one last thing we want to do for this function, and it's to determine the domain and range. Remember that the domain of a piecewise defined function consists of the x values that are in each of your pieces. So start by drawing a number line. We'll now illustrate the x values that are in each of these pieces. Our first piece consists of x values less than -2. So let's put down -2, put an open circle at -2, and highlight everything to the left. Our second piece goes from -2 to 1. So let's put down 1 on our number line. And what we want to do is we want to include -2, but exclude 1 and highlight everything in between. Lastly, our third piece starts at 3 and goes off to infinity. So we'll have a solid point at 3, and we want to highlight everything to the right. So looking at what's included in our number line, we see that our domain goes from -infinity to 1, and then it goes from 3 to infinity. To determine the range of our function, we want to look at our graph and determine what y values our points have. To find the lower bound, we want to look for the lowest points in our graph. The lowest part of my graph here have points with y value -1. So our range begins at -1, and then to determine the upper bound, we want to see if there's a highest point on our graph. But if we trace our graph to the right here, we see that the graph goes up indefinitely, so the upper bound for our range is infinity. So the range for this function is -1 to infinity. So in this video, we looked at more examples of piecewise defined functions, and we got more practice evaluating them, graphing them, and finding their domain and range.